Why hello, lovely humans, Jen Foxbot here. Welcome to another edition of Math Mondays. Da 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 da, yeah! Alright, thank you for joining me today. I am very excited. We are going to be covering geometric series. Yes! So, this is part of the sequence of videos that is going to build up to Fourier series. You don't have to get all the way there if you don't want to. That is totally fine. But if you're interested, I would definitely recommend checking out Simple Harmonic Motion and watching that before this video. Although this is a little bit unrelated, but that's okay. Related to Fourier series. Okay, so what is a geometric series? That's kind of a funny and big term. So basically, a geometric series is a sequence of numbers that goes on for a very long time, and it has a certain special pattern. So for example, 2, 4, 8, 16, what's 16 times 2? 32, etc. That is a geometric series. Or 1, 2/3, 4/9, 8/27, etc. That's a geometric series. And you know me, I like talking in terms of general formulas. And so we can think of a geometric series in the general form as something like this, where you have AR squared, AR cubed, etc. In this case, the ellipses just mean it keeps going forever and ever and ever. And in mathematics, we say forever or forever plus 1 or forever plus 2 is infinity, represented by a cute little sideways 8. Yeah! All right, so these are all examples of geometric series. Let's look at this in particular and ask the question, how do we find the sum of infinite series? That seems a little counterintuitive, but wait, there are some cool math tricks that we can use to find the sum of an infinite series. So let's look at the third example first, because it's the most general. So let's say what we're looking for the sum of a series that has n number of terms. So our series was A plus AR squared plus ... Again, lots of terms with this ... But we can also write the last few terms in our series because we know the pattern. So we will have AR to the n minus 2 plus, plus AR to the n minus 1. And so how do I know that the last term is n minus 1 and not n? Well, because we have a total of n terms. If this is n equals 1, this would be n equals 2. This is n equals 3. This is basically the second to last term, and this is the last term. And it's n minus 1 because of our pattern. So in this case, you could say that this is a times r to the 0. And so in this case, if we were to look at this general n minus 1, it's a little hard to read, plus a to the r n minus 1. It's a very large one. Okay, anyway. So you get, when n equals 1, you get r equals 0. When n equals 2, you get r to the 1. When n equals 3, you get r to the 2. And so if you were to plug in the value of n in here, you would get these numbers. So 3 minus 1 is 2, 2 minus 1 is 1, 1 minus 1 is 0. Cool, okay. So now we're like, wait a second, how do we add up an infinite number of terms? I don't have that much time in my life, let's be real. And I would agree. Let's look at these cool math tricks that we can do. So what I'm gonna do is I'm gonna multiply both sides by r. Super cool, right? So we'll say r over r times this whole equation. And what we're gonna get is r times s to the n equals a times r plus ar squared. This is going into this equation, plus ar cubed plus ... plus ar to the n minus 1. This term has an extra set of or an extra r in it. So one of the n minus 2 becomes an n minus 1, and the last term becomes a to the r to the n. Pretty cool, right? Okay, so we're not quite done yet. Now what we want to do, I'm going to erase this, is subtract this second equation from the first equation and try to solve for the sum Sn. And so what we get is, on the left side, we get S of n minus r to the Sn. That's pretty straightforward. And to the right side, don't panic, it actually works out really well because there's a bunch of terms that cancel. So remember, the subtraction sign applies to all of these, so all the pluses become minuses, so you get a little negative up here, etc. And so now we can go through and cancel terms that are the same. So I'm going to erase that. We don't have another a term by itself, so that will come down, but pretty much all of these other terms are going to cancel. This one will cancel with this next term, which I didn't write down because you got the picture. This term cancels with this term just before, whoopsies. This term cancels with this term that's just before here. And then this term cancels with this term. And we're left with a negative ar to the n. What? So cool, right? So we took a geometric series that had an infinite number of terms, effectively. We don't know what n is. N could easily be infinity. And that's okay, because it doesn't matter what n is. N can be any number. Totally fine. And now all of a sudden we have a very simple equation. And so we can solve for the sum of our geometric series. So we can pull out s to the n, and we get 1 minus r equals, we can pull out an a times 1 minus r to the n. And now we can solve for Sn by dividing both sides by 1 minus r. So Sn equals a times 1 minus r to the n divided by 1 minus r. It's so cool! Now we have a general formula for finding the sum of a geometric series with any number of terms. So n could be infinity, and we can apply this equation. N could be 5, and we could still apply this equation. This is really handy when you have really large values of n. When you only have 5 terms, we could do those by hand, but this still might be faster. So whenever you have a geometric series that looks like something of this form, you can use this formula. Really cool, right? So now you're probably like, well, wait, who cares? Why does this matter? Let's look at a specific example. I want to hold on to this, and so I'm going to write it up here to save for later. So Sn, the sum of our geometric series with n number of terms, equals a times 1 minus r to the n divided by 1 minus r. Okay, and I'm going to erase this and give us some more space to tackle a real-world problem. So in that second example, we had the terms 1, 2/3, 4/9, 8/27, etc., ... And let's say that that represents the bounce heights of a ball. So then we ask, okay, what is the total distance that the ball traveled? We know that we have our fancy measuring apparatus that measures the heights of the ball. And so we would say, okay, well, the sum, again, we have n number of terms, equals 1. That was the first height. We dropped the ball. We'll ignore the drop, I guess. And so, well, actually, let's say we drop the ball at 1 meter, and we're asking what is the total distance that the ball traveled. So to be fair, it traveled 1 meter from our drop height, and then it bounced to a height of 2/3. We'll just say meters, because I like the metric system. It's a little easier than the American system. I love my country, but I love the metric system also. So anyway, okay, so now the ball bounces back at a height of 2/3 meters, and it drops 2/3 meters, bounces back at a height of 4/9, drops 4/9 meters, bounces back at a height of 8/27 meters, and drops that amount. So basically all that is to say that when it bounces back to a certain height, it also travels down. So we have to multiply each successive height by 2 to get the total distance traveled. So we have 2 times 4 ninths plus 2 times 8 27ths plus ... We're gonna just focus on these terms for now because, like we found, we can make we can do a good analysis without having to write down all of the terms. Okay, so now what we can do is we can simplify a little bit, and we can say 1, and we can pull out a 2. So each of these terms has a 2, so we say, well, that's a funky 2. 2/3 plus 4 ninths plus 8 27ths plus ... Okay, and now we can say, oh, look at that! We have a little geometric series in here. So let's ignore this for a second and focus on the sum in the parentheses, which I'll represent with a P instead of an N. And let's apply this geometric sum formula to these terms, because this is where it keeps on going. So we need to figure out if this sum will converge to a specific number or if it becomes infinite. Okay, so in this case, A is 2/3, and our ratio, or R, is also 2/3. So we have 2/3 times 1 minus 2/3 to the n divided by 1 minus 2/3. And this is a messy equation, and so let's simplify by multiplying the top and the bottom by 3/3, because that's just 1. And so this, the 3's cancel, and we get 2 times 1 minus 2/3 to the n. And the bottom, we'll get 1 times 3, 3 minus 2. Oh, look at that, it goes to 1. That's handy. So then we just get 2 times 1 minus 2/3 to the n. Oh, that's an n. Okay. Divided by 1, but don't need to write that. Okay, so now the sum in parentheses is just this. And now we can say, okay, well, as n gets bigger, as n goes up, 2/3 to the n goes down. And at a certain point, this is going to be a very, 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 very small number. Basically, when we compare that number to 1, it's going to be pretty much 0. If we were to subtract this very, 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 very small number from 1, we would get like 0.999999999999999, etc. You get the picture. And so, especially as a physicist slash engineer, we round up. That's fine. And so in this case, we can say, well, okay, we know that the ball, sure, is going to keep bouncing microscopically, but do we care? Does it affect the total height? Not really. I mean, maybe if we were working in quantum mechanics, we would care, but for our purposes, as n gets larger, these fractions, this 2/3, contributes less and less and less to the total height of the ball, to the point where it doesn't actually affect our calculation. So we can say that the 2/3 goes to 0. Boom! And so now the sum in parentheses is just 2 times 1, which is just 2. Huzzah! And so, I'm going to erase this part. I'll keep that down there. And we'll say now the sum, the total height of our ball, is just 1 plus 2 times 2, which is 5 meters. Boom! Pretty radical, right? I love this because this is accurate. If this was a real problem, we would get a measured distance of 5 meters. And even though we only kept 3 terms in this potentially infinite series, our answer is still valid. There's a lot of really cool math tricks when we're talking about series and dealing with infinite numbers of terms. So what I really want you to understand, and I'm going to check my notes so that I get the verbiage right, is that after a certain number of bounces, the remaining infinite terms contribute less and less to the total height. So we can neglect them, and it's still accurate. And this comes into play with Fourier series very, very importantly. So yeah, okay, I'm gonna leave it there for now. Please let me know if you have any questions about geometric series or any other math topics in general. And if there are particular issues within the topic of Fourier series, I'm also going to cover the complex number plane because that's also super important. And in that, we'll deal a little bit with sine and cosine. But if you want me to cover sine and cosine in a more basic video, I'm happy to do that as well. Let me know what your interests are and we'll tackle it together. All right, thanks very much for watching and we'll see you next time. Bye!